Hi students, let's see the lesson 5, Rankine cycle. This cycle is called Rankine cycle because the name of the scientist who designed the cycle called Rankine. There are three types of Rankine cycles. The one is a simple Rankine cycle, next one is a reheating cycle, and the last one is a regenerative cycle. This reheating and regenerative cycles are improved methods of Rankine cycle. First, let us see the simple Rankine cycle. All these Rankine cycles are used in thermal power plant or steam power plant. In simple Rankine cycle, we consider only four components. One is boiler, steam turbine, steam condenser, and the condensate pump. Between 1 and 2, the expansion takes place in the steam turbine. The expansion is isentropic expansion. Between 2 and 3, constant pressure heat rejection takes place in the steam condenser. Between 3 and 4, isentropic compression takes place in the pump. And between 4 and 1, constant pressure heat addition takes place in the boiler. And this is what's shown in the TS diagram. So 1 to 2 is isentropic expansion, 2 to 3 is constant pressure heat rejection. Here also temperature constant because the phase change occurs. And between 3 and 4 it is isentropic compression process, and between 4 and 1 it is constant pressure heat rejection in the boiler. And the same thing is shown in HS diagram. This is otherwise called Molier chart. Here between 1 and 2 isentropic expansion, and between 2 and 3 it is constant pressure heat rejection, because in Molier chart or HS diagram these lines are nothing but constant pressure curves or constant pressure lines. So similarly between 4 and 1 the pressure remains constant, and between 3 and 4 it is isentropic compression in the pump, and between 4 and 1 it is constant pressure heat addition in the boiler. Now let us see how to find the efficiency of a Rankine cycle. It is as usual work done by heat supplied. Here work done means a net work done by heat supplied. This net work done we can find either the ratio between heat supplied and heat supplied minus heat rejected, or we can also find the difference between turbine work and pump work, because how much amount of work actually developed by the turbine and how much is the work input consumed by the pump, the difference is nothing but the amount of work output supplied to the generator of the power plant. Therefore, the efficiency of Rankine cycle is turbine work minus pump work divided by heat supply. Let's see how to find out the turbine work, pump work and heat supply. The turbine work in terms of enthalpy is H1 minus H2. During isentropic expansion, H1 minus H2, because H1 is greater than H2. And pump work we are going to find H4 minus H3. But this H4 we cannot find directly using the steam table, and hence another way of finding the pump work is delta P into VF3. This delta P is nothing but the pressure difference between the points 4 and 3. So therefore P4 minus P3 into VF3, where VF3 is the specific volume of the fluid which is at point 3. But the condition here is the difference between the pressure should be in kilopascal, and heat supplied is found the difference between H1 and H4, because here is a boiler, the maximum temperature is T1 and minimum temperature is T4. Therefore H1 minus H4 will give how much amount of heat is supplied in the boiler. Let us substitute the equations 2, 3 and 4 in the equation 1. We get the efficiency of Rankine cycle is equal to H1 minus H2 minus H4 minus H3 divided by H1 minus H4. Now let's see the reheating cycle. In order to increase the work output, we are reheating the exhaust steam which is leaving the turbine 1 or high pressure turbine. So here also the same formula we are going to use to find the efficiency of Rankine cycle: turbine work minus pump work by heat supply. And this is the TS diagram. Here 1 to 2 is expansion in the high pressure turbine, and 2 to 3 is reheating in the reheater, and 3 to 4 is expansion in the low pressure turbine, and 4 to 5 is heat rejection constant pressure in the condenser, and 5 to 6 is isentropic compression, and 6 to 1 is constant pressure heat addition in the boiler. This is what shown in the HS diagram. 1 to 2 is isentropic expansion, 2 to 3 is constant pressure heat addition in the reheater, and 3 to 4 is isentropic expansion in the low pressure turbine, 4 to 5 is constant pressure heat rejection in the condenser, and 5 to 6 is isentropic compression in the pump, and 6 to 1 is constant pressure heat addition in the boiler. The heat supplied Qs is equal to H1 minus H6 plus H3 minus H2. Heat supplied Qs is equal to H1 minus H6 plus H3 minus H2, because the heat addition in the boiler is H1 minus H6, and the heat addition in the reheater is H3 minus H2, and the total turbine work is H1 minus H2 in high pressure turbine plus H3 minus H4 in the low pressure turbine. The pump work is H6 minus H5. This pump work we can also find as usual delta P into Vf5, where delta P is P6 minus P5 into Vf5. So here the block diagram shows how does the reheating cycle works. 1 to 2 is isentropic expansion in the high pressure turbine, and between 2 to 3 reheating, 3 to 4 expansion in the low pressure turbine, between 4 to 5 condensation at constant pressure, between 5 to 6 isentropic compression in the pump, between 6 to 1 constant pressure heat addition in the boiler. By substituting the equations 2, 3, 4 in equation 1, we get H1 minus H2 plus H3 minus H4 minus H6 minus H5 by H1 minus H6 plus H3 minus H2. The third cycle called a regenerative cycle. Here, usually during a regenerative cycle, we used to neglect the pump work. So here, from the boiler, steam is supplied to the turbine. During expansion in the turbine, some amount of steam is taken for feed water heating or condensate heating. This is called regeneration. So the exhaust steam from the turbine goes to the condenser, where the exhaust steam is getting converted into a condensate. This condensate is supplied to the boiler. Before it is supplied, with the aid of feed water, we are going to heat, but the heat source is the steam itself from the turbine. So some amount of steam from the turbine is taken for heating this condensate, and then it is supplied to the boiler, by which we are increasing the efficiency of the Rankine cycle. So here 1 to 2 is expansion. Let us assume during this cycle 1 kg of steam is taken for consideration. So this 1 kg is getting expanded between the point 1 and 2. At point 2, since m kg of steam is taken for feed water heating, the remaining is only 1 minus m kg. So now 1 minus m kg is getting expanded in the turbine within the points 2 and 3. This 1 minus m kg of steam is getting converted into a condensate, and then it is sent to the feed water heater, and this 1 minus m kg of condensate and m kg of steam both gets mixed up, and it is becoming 1 kg of feed water. Again it is supplied to the boiler and getting converted into steam. That steam is supplied to the turbine. The same thing is shown in the HS diagram. Between 1 to 3 expansion, but between 1 to 2 1 kg of steam is getting expanded, and between 2 to 3 1 minus m kg of steam is getting expanded, because at point 2 m kg of steam is taken for feed water heating. Now, as usual, the efficiency of Rankine cycle is work done by heat supplied. The work done means net work done. Net work done means the difference between turbine work and pump work. But since we neglect the pump work in the case of a regenerative cycle, the efficiency of Rankine cycle is only the ratio between turbine work and heat supply. So the heat supplied is H1 minus H5, which is taking place in the boiler, H1 minus H5, and the total turbine work is H1 minus H2 plus 1 minus M into H2 minus H3, because between point 1 and 2 mass is 1, therefore 1 into H1 minus H2 plus between 2 and 3 the mass of the steam is 1 minus M, that is what, 1 minus M into H2 minus H3. This one we can consider, or we can neglect also. There is no change, much difference. So we get equation 2 and 3. Let us substitute equation 2 and 3 in the above equation 1. We get the efficiency of Rankine cycle as H1 minus H2 plus 1 minus M into H2 minus H3 divided by 1 H1 minus H5. So here H1, H2, H3, H4 and H5 you can find either by using the steam table or Mollier diagram or HS diagram. But in order to find this M, we are going to use the energy balance. The energy balance here is at point 5, at the enthalpy H2 and the mass m kg of steam is entering, also the enthalpy of liquid is 1 H4 and the mass is 1 minus m. So 1 minus m kg of H4 and m kg of H2 both are getting mixed up together at point 5, which is called H5. Therefore H5 is equal to m into H2 plus 1 minus m into H4. With the aid of that energy balance, m into H2 plus 1 minus m into H4 is equal to H5, we are going to find out the value of m. Let us multiply this 1 minus m and H4, we get 1 into H4 is H4 minus m into H4 is mH4. So we are going to bring this H4 this side, only m terms this side. We can take m commonly outside, we get m into H2 minus H4 is equal to H5 minus H4. Therefore m is equal to H5 minus H4 divided by H2 minus H4. Once we find H1, H2, H3, H4 and H5 with the aid of steam table or Mollier chart, you can find out M. By substituting all the values, we can find out the efficiency of Rankine cycle. So it is a known truth that the efficiency of reheating cycle and Rankine cycle will be greater than the efficiency of a simple Rankine cycle. Thank you.